All right, well, welcome to our third and final part of this video series dealing with tanks and fluid levels in tanks. And so in this final part, we're going to be asking the question, if we were to set a tank at a particular set point and we say we want this tank to always be at this fluid height, how do we go about doing that? And so in part C here, we're going to use a proportional controller to control the liquid level in the third tank. And the way we're going to do it in this case, there's multiple ways we could do it, but in this video, we're going to do it by adjusting the flow going into the first tank. So we're gonna put a set point for the third tank, and then we're going to adjust the flow coming in to the first tank. And so we're going to derive a differential equation describing this controlled response. And then lastly, we're going to model out the dynamics of for different proportional gain values. We're going to simulate the response of our system to a 10% set point increase in the liquid level in the third tank. So we're going to increase what the height is in the third tank. We're going to do a 10% increase as our set point, and then we're going to evaluate what different proportional gain values does to try and get our tank to that set point. And so let's go ahead and start off by going back to our three tanks that we talked about in part B. And so we have our three tanks here and our flows going into each. Now, the additional thing we're adding here is if we want to say, here's our set point in tank 3. What we're saying we're doing here is we're going to do that by manipulating the flow coming in to the first tank. So let's go ahead and model out how we're going to do that. If we have our flow, well, if we have our tank 3 set point that we want to maintain, and here we're saying a 10% increase of our current height level in the tank at the steady state, how are we going to maintain this? That's the question here. So we're saying we're going to manipulate the flow coming into the first tank, and so Q in, well, now the question is, what does Q in equal? So we know at least that we're dealing with, in any particular situation, we have a particular height for our set point. That part is fixed, so we know what we want our set point to be. It's the H, it's the fluid level in that tank that's going to be changing. And we want to evaluate the gap between our set point that we've determined and whatever the current ever-changing height is in the tank. And so this is continually assessing what is the difference between the two. And this is going to be in meters cubed per second because that's our flow rate coming in. This is dealing with meters. Now the question is, what do we do? So here's where our proportional controller comes in, which is our KC. We're calling that our controller gain. And that's what we're trying to show here, our proportional controller, our proportional gain value. And so what KC is it's a proportional constant. So it's saying, okay, we have our difference here, right here, and this is evaluated and saying, what do I need to multiply this by in order to then change this to? Now, what we're basically saying is, if the height in our tank is, let's say, greater than the set point needs to be, well, then this is going to be a negative value. This is going to multiply by this, and it's going to decrease our flow by a constant value of whatever Kc is. And so if this is higher than this is now a negative difference multiplied by whatever proportion constant we give it. That's going to then decrease the flow in, which is what we want, because then the increased height, which is above our set point, is going to then eventually decrease and get closer to our set point. If this is lower than what our set point is supposed to be, well, then this is going to be a positive value multiplied by a proportion constant, our controller gain there, and that's going to then increase the flow, the Q into the first tank. Now this would be fine, except this is incomplete in the sense that this is relative into itself, but it's not taking into account that there was already a steady state flow going into tank 1. And so if we don't do it relative to the initial steady state flow, we're going to get a significantly lower value than what we're shooting for, because it's not taking into account that there was an initial flow coming into the first tank. So this is the differential equation that we're going to need to code out and model, and then we're going to, going back to here, so we've derived the equation of what we're dealing with for our proportion control, and now we're going to simulate different Kc values and seeing what is the dynamics of the process there based on the different Kc values, and are we going to have significant oscillations? How close to our set point are we going to get? And so that's going to be the next thing that we move on to here. All right, so what we're going to do then is we're going to pull up our 3 tanks from part B of this video, and we're going to add our controller gain, our proportional control, to this, and go ahead and see what are the pros and the cons, and simulate the dynamics of using a controller gain. So our parameters are going to be largely the same. We're going to add our set point, and we determined that the set point is going to be 10% set point increase of the liquid level in the third tank. So that is going to be our H naught, whatever the steady state was in the third tank, with a 10% increase. So let's go ahead and add that to it. And then here in defining our right-hand side, the only thing that has changed is this equation right here. So if we go back and look here, we see that this equation right here is now our new Q in using our controller gain. So let's go ahead and code that in. So we've got Q in equals Kc times H3 set point minus the tank in the liquid level in the third tank, and then plus our initial Q in value at the steady state parameters. So let's go ahead and run that. Okay, so now we need to define Kc, which let's do this. Okay, first let's go ahead and let's just get an estimate of what our initial fluid height is and what our, okay, so here is our initial height in the tank at steady state. It's our HO. Now this is the set point with a 10% increase. We're aiming to get to 5.61 meters in our third tank. So we're wanting to keep controlling the flow either with an increased flow into the first tank or a decreased flow into the first tank, so that we shoot towards getting a 5.6 roughly meters as our defined set point, which is our 10% increase for the third tank. So this is what we're going to shoot for. So let's go ahead and give Kc a value, let's say 0.01 to start, and let's run each of these, see what our new situation is. Okay, so here we see, again, we anticipate the first tank is going to be the first one to climb because it's the one that's receiving the increased flow, and then tank 2 and then tank 3 responds last, and they all eventually steady back out, but we have it as 5.3. It's steadied out at 5.36, which is not the set point that we were hoping to achieve. So let's go ahead and let's decrease it here. Okay, so less oscillations, less extremes with a lower, because the Kc value is the proportionality constant that we're multiplying each difference by is smaller. We would anticipate less extremes, but we also get a lower set point. So it's bottomed out. It's steadied out at 5.14, so that's even lower. So let's go a little bit higher than 0.1, that's right, 0.02. Okay, now getting more extreme with our oscillations, not good for dynamics. 5.45, still not our set point. so as we can already see, the problem that we're hitting is each time there's a difference between the set point that we've defined for the third tank and the fluid level that's actually in the third tank, whether a decrease or an increase, that proportionate constant, as the Kc, as the gain value is larger, it's creating bigger swings, either with an increased swing or then, oh, we've overcorrected, so now we're going to ratchet it back a little bit, and then, oh, now we're way low, and then so we get these big oscillations that are occurring here. And it's a bigger oscillations, 5.48, that's not even that much greater, and it's still not our set point of 5.6. So we're running into a continual problem with where we're getting these big oscillations in our process. 5.5, that's close, but still not the set point. And then the downside is that we're doing it at the expense of ever increasing oscillations. I mean, look at this. Now we're all the way up to 6.5 meters in the tank, all the way down to 4.7. And then it just eventually, way over here, it 5.54. So it's still not even our set point. And let's see what it caps out at. Eventually, we're going to hit a point of no return, and so we've surpassed it here. So there's a particular point in which we've got our critical value, in which our oscillations will just stay and carry on forever. They won't increase any further, but they also won't decrease, and it'll just stay at this constant oscillation on into forever. That's our critical point that we can't pass. Otherwise, we run into this where the corrections just keep overcorrecting, and that overcorrection corrects an overcorrection and overcorrects it even further and on into infinity. And this, as we see, let's just go ahead and extend the time even further. Well, that's probably too much. Let's say, I don't know, 7,500 seconds. Yeah, it's continuing. It's going to continue. It's showing no signs of decreasing. And then eventually we might hit a point where it just it bottoms out. Tolerances are too small. It can't, the oscillations, if it become too big, it's hit its max, it's hit on into infinity. And so let's try, what was a decent value? 0.1, well, we didn't try this. Let's try 0.15. So pretty large oscillations, but at the expense of never hitting our set point. And so what this video is showing is we've modeled the proportion control using our Kc, our gain value, as our proportionality constant, which is multiplying any difference between the set point that we've defined and the actual fluid level, either greater or lower than the set point, and multiplying that, and then increasing or decreasing the flow into the first tank accordingly. But the downsides is that we can never end up reaching the set point that we want. The oscillations either become increasingly extreme and get closer, but still not quite to our set point, and not even hitting our set point is at the expense of just these big oscillations happening in our process, which we don't want. And then if we go really low again, before closing this out, even if we set our gain value really low, we have much smaller swings, which was anticipated, but at the expense of being even farther from our set point. And so these are the downsides of the proportion-only control. And then in which case you would move on to other ways of controlling, like a PID and using error and things like that. But this video is just trying to model the different things that can happen with the Kc values, and what happens accordingly when we increase or decrease those Kc values, our gain values, to try and get to our set point of controlling the fluid level in a tank. Thank you.